Hello, and welcome to Chapter 1, Section 6. Today we're talking about limits at infinity. So, limits at infinity just means we're finding the limit as x approaches either infinity or negative infinity like this. So really what we want to know is, what is the end behavior of the graph? As you go all the way to the right or all the way to the left of a graph, what y value is your graph approaching? So then what's important for us to look at is then the horizontal asymptotes. Because if the graph has some sort of horizontal asymptote, then we know that whatever line it is, there's the graph that's going to get really close to it as it keeps going either to the right or to the left. And that's why it's important to know what the horizontal asymptote is. So we started looking back at horizontal asymptotes like back in Algebra 2. That's when you first learned about them. And there was like a method to find out what they were. So this applies mostly to rational functions. For rational functions, you wanted to look at the degree on the top and the bottom, because rational means, fraction. So the degree was the highest exponent. So on top, if the degree on top is smaller than the bottom degree, then that means, like, when you divided, the value of whatever was on the numerator of the fraction would increase slower than the bottom. And so when that's the case, then you end up with a horizontal asymptote of y equals 0. If the top degree is the same as the bottom degree, then we could assume that the increase on the numerator and on the denominator was about the same. So really all we had to do was divide the leading terms, and then that'll give us the horizontal asymptote. The last method was if the top degree is bigger than the bottom degree, then in that case, there's no horizontal asymptote. It's actually a slant asymptote. And if it's a slant asymptote, then that means your graph is either increasing forever or decreasing forever. So it's like going downwards or going upwards on either the left or the right. So basically, as a visual, if we have a horizontal asymptote at, like, let's say y equals some number k, then the limit as x approaches infinity, meaning if we go all the way to the right, then that limit is going to be k. And if we looked at the limit as x approaches negative infinity, going all the way to the left, then that limit is still going to be k, because that's where the horizontal asymptote is. Alright, so let's do a whole bunch of examples. So for my first example, I have the limit as x approaches infinity of -1 over x squared. So first, we have a rational function, so I want to determine what is the degree on top, what is the degree on the bottom. So remember, the degree is the highest exponent. On top, we don't have any x's, thus no exponents, so 0 is the degree on top. On the bottom, we have the highest exponent of 2 for the x squared. So that would mean that the bottom is bigger than the top in terms of the degree, and when that happens, the horizontal asymptote is y equals 0. So I'll just jot that down. Horizontal asymptote is y equals 0, which means that for this graph, as we go towards the left and to the right, the y value will always approach 0. So the limit of this function is going to be 0. For my next example, I have a similar one, except this time I'm looking for a limit as x approaches negative infinity. So this time we're looking at the left side of the graph of the function 5 minus 10 over x cubed. So first, I have like two separate things here. I have the 5 here, and I have the -10 over x cubed. So I'm just going to focus on the fraction first, because, that's where we usually have the horizontal asymptotes. So the degree on top, since it's just a 10, there's no x's, again, is 0. The bottom, the degree is 3. So for that, the horizontal asymptote, again, is going to be y equals 0, because the bottom degree is bigger. So if that's the case, then I know that for just this part of the limit, that's going to be 0. But then I have that 5 there, which kind of changes things. So if we were to just focus on the limit as x approaches negative infinity at 5, well, 5, if you just think of it as like y equals 5, it's just a horizontal line. So in both directions, the left and the right, then the y value will just be 5. So the limit here of just the 5 is still 5, minus the fraction we said the limit was going to be 0. So our final answer is going to be a limit of 5, because 5 minus 0. Another way to think about this is kind of like splitting this up into two separate limits. If I were to find the limit of x as x approaches negative infinity of 5 minus the limit as x approaches negative infinity of 10 over x cubed. Because then this part of the 10 over x cubed would give me 0, this part would give me 5, and that's really all we're doing. So whenever you see like multiple parts to your equation, you can just split it up like that. For my next example, I don't exactly have degrees on the top and the bottom. So if you look at the function 3 over e to the x power, the degree on top is still 0 because we don't have any x's, but then on the bottom, I don't really have an exponent, like x is my exponent. So if we're saying x approaches infinity, we're basically saying x is going to be a bigger and bigger number no matter what we plug in. So think of e to the x as like e to the power of a really big number. So thinking about that, it's kind of like we're doing 3 over e to the infinitieth power if we were to plug in infinity for x, which e to the infinity is a huge number. So the number 3 over a huge number ends up being a fraction where the top number is really small, the bottom number is really big. So if you have a really big denominator, like think 3 over 100 million, that's basically a really, really small decimal, pretty close to 0. So it's kind of like the degree where on the bottom you have a much bigger degree, then you approach y equals 0 again. For my next example, we have something really similar. So this time I'm still doing the same function 3 over e to the x power, but this time I'm looking at the limit as x approaches negative infinity. So if we kind of look at this like we did before, where we just plug in negative infinity this time in for x instead of just positive infinity, keep in mind a negative exponent really means you're turning that into a fraction. So it's kind of like you doing 3 over 1 over e to the infinitieth power, because that negative exponent turns it into a fraction. And if we rewrite this, then, because complex fractions are hard, if we did 3 divided by 1 over e to the infinitieth power, then I can rewrite this as 3 times the reciprocal, which would be e to the infinity over 1, really. But 3 times e to the infinitieth power is like 3 times a really big number, which is just going to be a really big number. So infinity would be the limit. So for my next example, I've got the limit as x approaches infinity of 2x minus 1 over x plus 1. And looking at the degree on the top and the bottom now, we have x's on both the top and the bottom. We have 2x, so x to the first power would be the biggest degree, and then x to the first power again would be the biggest on the bottom. So if those are the same, we were saying earlier that you would divide the leading terms. So my leading terms here would be the 2x and on top, and then the x on the bottom. So if I divide that, the x's would cancel out, and I would just be left with 2. So the horizontal asymptote for this function would be y equals 2, which is why the limit is also 2. For my next example, I've got the limit as x approaches infinity of 2x cubed plus 5 over 3x squared plus 1. So looking at the degree on top, the highest exponent is a 3. On the degree on the bottom, the highest exponent is a 2. So based on my degrees, since the top is bigger, that's when you're going to not have a horizontal asymptote, you're going to have a slant asymptote. So if it's slant asymptote, your limits are basically going to be either positive infinity or negative infinity. Because think about what a slant asymptote looks like. If we had some asymptote here slanted this way, and then my graph would be either like this way, or something like that. Then if I'm looking for the limit as x approaches infinity, we're saying like everything to the right side. So going towards the right side of my graph keeps going upwards forever and ever and ever, and that's why you either get positive infinity or negative infinity. If we were talking about negative infinity for my limit, then I'd be talking about the left side where it's going downwards, so it'd be negative infinity. So for this graph, for the 2x cubed plus 5 over 3x squared plus 1, I don't know if this is the actual graph. I just kind of drew something out for an example. So here, what we want to do is actually kind of like before how we divided out our first terms. I would take my 2x cubed over 3x squared. If I divide this out, I end up canceling an x squared on the top and the bottom to get 2x over 3. So now when you plug in infinity, it's kind of like you doing 2 times a big number divided by 3, which is still going to be a huge number, because if you multiply anything by a huge number, you're going to get a big number. So the limit would be infinity here. For my next example, it's again going to be the same equation, just this time I'm looking at the limit as x approaches negative infinity. So on the left side of the graph, if we were to graph this out, I'm going to do the same thing as before because I know the degree on top is bigger again, so that this is going to be a slant asymptote. So if I divide out my first terms, my leading terms, I end up with 2x over 3 again. And plugging in like negative infinity in for x then, 2 times a negative infinity would be like a negative big number. So, and then dividing by 3 doesn't change a whole lot because it's still going to be a big number, just negative. So this time it'll approach negative infinity. All right, let's do another example. So this time I have the limit as x approaches infinity of sine x. So notice how this time I don't have a rational function. This is just, there's no fractions here, it's just sine x. So for this one, think about the graph of sine x. If you were to graph it out, this is the one where it does like, you know, the wave, all the way forever and ever. Okay, so if we're looking at the limit as x approaches infinity, we're saying all the way to the right of this graph, what y value will this approach? Well, it'll keep fluctuating and oscillating between 1 and negative 1. So all of the numbers between 1 and negative 1, because, you know, the amplitude of a sine graph is between 1 and negative 1. If it keeps switching between those numbers, then we don't know exactly what value the graph will get close to. So in this case, it would be does not exist because it keeps oscillating between the two. All right, this is my very last example. So this time I have the limit as x approaches negative infinity of sine x over x. Okay, so we just said sine x, it's going to oscillate between 1 and negative 1 because, you know, the waviness. But then because we have it as a fraction now, if we know on top, if I were to plug in negative infinity, sine of negative infinity, whether it was positive infinity from before or negative infinity now, it's still going to fluctuate between 1 and negative 1. So I'll kind of just state 1 or negative 1. But then we have negative infinity on the bottom of the fraction. So on top, I've got some number, 1 or negative 1. Then, but on the bottom we have a really big number that's just negative. So if we have a fraction where the denominator is really big, even if it's a negative number, it'll still, my overall fraction will still be a really small number, actually getting close to 1. It's kind of like when your degree on the bottom is bigger, then your horizontal asymptote is going to approach 0. Because we have some small number on top, either the 1 or the negative 1, over a really big number. So that's going to get close to 0. All right, so when we're dealing with limits to infinity, we basically want to think of it as plugging in a really big number and then see what you get. That's kind of the overall strategy. All right, thanks for watching. That's it for this section. Have a great day. Bye.